In this video, I will talk about using artificial intelligence in the context of education. In particular, I want to share with you research on how techniques from explainable artificial intelligence can help to bring predictions made by AI algorithms to educational practice. This research was done for a particular application domain within education, student advising. So let's first try to understand the context of this application. Imagine a student who is deciding on which program to subscribe to at higher education, and this student is having doubts and therefore scheduled an appointment with a student advisor. The student wants to know if she can be successful in engineering, how she can better prepare herself, and what her strengths and weaknesses are compared to the required starting competencies of the program. The student advisor is very eager to understand what drives the student, what the student is doubting about, what the type of advice could be most supportive to the student, and which actions the student could undertake. The goal of the research I'm sharing with you is to incorporate AI predictions into such an advising conversation. Data regarding what made past students successful in the program can be very informative when advising new students. Therefore, bringing AI predictions using such data into the academic advising conversation could support the professionalization of student advising. If we have data available of past students, we can train AI algorithms to predict if a new student will be successful or not in the program. These predictions can be provided to the student advisor, such that the advisor can incorporate this information into the conversation in a way that the advisor finds appropriate. However, imagine that the AI algorithm states, "Warning. The probability that a student will be successful is only 23%. What can the advisor or student do with this information? Why is the algorithm predicting this? Can the predictions be trusted? And if the prediction is accurate, does it provide information regarding the actions the student can take to be successful in the program?" Incorporating AI predictions can potentially alienate users and create mistrust or overtrust in the algorithm. Furthermore, GDPR states that the users have the right for explanations of predictions. So what can be done? This is where explainable AI can come to the rescue. Explainable AI can make the complex internal mechanisms of machine learning models transparent for users. Explainable AI can hereby increase the understanding of AI outputs and the trust of users in these outputs. Beware, however, this trust should be appropriate. The user should not be more suspicious than needed when the predictions are, for instance, very accurate, but should be very critical about the AI predictions if the AI predictions are also doubtful. Explanations of predictions of student success could help to understand the potential characteristics and phenomena that make students successful or fail. Such explanations can help to reflect on potential ways to improve and therefore help the advisor to formulate recommendations for actions the student can undertake. In our research, we started from data of 1,824 engineering science students from 4 academic years. The data contains information about the prior academic trajectory and achievement and learning and study skills. The prior academic trajectory and achievement data includes the number of math hours students took in secondary school, the grades they obtained in mathematics, physics and chemistry, and their self-reported effort level for obtaining these grades. Also, their self-reported pressure preference, it is their preference to wait for a deadline to undertake action, is in the data. The data on learning and study skills come from a validated questionnaire that measures motivation, time management, concentration, anxiety, and use of test strategies. This data is used to train and validate a predictive AI model that predicts whether a student will be in one of three categories. No risk, meaning that the algorithm believes that the student has a high probability to be successful in the program. Medium risk, meaning that the algorithm sees a moderate risk that the student will not be successful. And at risk, meaning that the algorithm thinks that this student has a high risk to be not successful. In our case, we used the feed-forward neural network, where we used 80% of the data for training the algorithm and 20% of the data to validate the algorithm. The validation showed that the AI algorithm can predict whether the student is in no risk, medium risk, or at risk with an accuracy of 78%. Now the crucial step: using explainable AI to explain why the AI algorithm believes that the student is predicted to be at no, medium, or high risk to be not successful. To this end, we used a technique called LIME. This is an acronym for Local, Interpretable, Model-Agnostic Explainers. So what does LIME do? First, we tell the AI algorithm to predict for a new student whether he or she will be successful or not. What the AI algorithm actually constructed are very complicated decision boundaries between the no-risk, medium-risk and high-risk categories in a very high-dimensional space. LIME will, for the student we are making a prediction for, create a local linear approximation of these decision boundaries. With this local approximation, LIME can then provide information on how strongly particular student characteristics contribute to the predicted probability of being at risk. For instance, imagine the AI algorithm predicts that our student has 57% probability to be at risk. LIME can then show that the student's low level of motivation and the low levels of effort were the most important characteristics for the predicted 57% probability to be at risk. At the same time, LIME can also show that the hours of mathematics was not important for the algorithm to predict the 57% probability to be at risk. As such, LIME explains why the AI prediction that was made by showing how important particular student characteristics were to make the prediction. In our research, we have designed an advising dashboard that supports the advising conversation. The dashboard first shows for a particular student the student characteristics. Additionally, it shows the AI prediction by indicating the percentage that a particular student is predicted to be at risk, moderate at risk, and no risk. The explanations are also integrated in the dashboard. By clicking one of the three risk categories, the dashboard will highlight the student characteristics that contributed most to the prediction of that risk category. For instance, if the advisor wants to understand why the AI algorithm predicts that a student has a 12% probability to be in the no-risk category, the advisor can click the green circle. The dashboard will then highlight in green the categories that contributed most to the no-risk category. The more important the characteristic is for the prediction, the darker the shade. For instance, here you can see that the hours of math the student took in secondary education and the results obtained in math, physics and chemistry are most important for the AI algorithm to state that the student is in the no-risk category with 12% probability. To research the impact of the advising dashboard, we performed a user study with student advisors and assessed how they used the predictions and explanations and their level of understanding and trust in the predictions and explanations. Our results showed that the dashboard with explanations can actually support the integration of AI predictions in advising practice. The explanations contribute to the awareness of advisors on the importance of particular student characteristics for student success, and very importantly, they trigger reflection with the advisors. The explanations show to support the development of appropriate trust, so no mistrust or overtrust, in the AI predictions. We also found that in case of cognitive dissonance, where the AI predictions do not match the beliefs of a student advisor, the advisors more easily start mistrusting the algorithm rather than their own beliefs. This is very interesting for future research in cognitive sciences. Additionally, we also found that care should be taken to not create cognitive overload with all the information and visualization provided to the advisors. This calls for future research in human-computer interaction. To summarize, in this video I have shown you how techniques from explainable artificial intelligence can help to bring predictions done by AI algorithms to educational practice. I hope this helped you to understand the challenges that bringing AI predictions to practice can bring, and how explainable AI can be part of the solution. Thank you for watching.